Today we're going to jump into the world of factoring, and factoring is, for the most part, the undoing or the opposite of the distributive property. We're going to start by doing some factoring that we did back in 6th grade, and that's prime factorization. And if you remember, that's like creating a factor tree of finding all the prime factors of the number in question. So if I want to find the prime factors of 98, I usually start at the beginning with 2. And I know that 2 times 49 is going to be 98, so I put 49 on that other branch. And then I say, okay, what are the prime factors in 49? That's 7 and 7. Whoops. 7 and 7. So 98 is equal to 2 times 7 squared. And that's the prime factorization of 98. Now, the greatest common factor, or what we'll term it as GCF, is the largest number that divides evenly into 2 or more numbers. So what I want to do now is show the prime factorization of 128 and 60 and then state the greatest common factor of those two numbers. So let's start with the tree for 128, and we'll go 2 and 64. I'm just going to break it all down and go 2 and 32, 2 and 16, 2 and 8, 2 and 4, and 2 and 2. So you'll see at the end of the tree I have 1, 2, 3, 4, 5, 6, 7 2s. So 128 is 2 to the 7th power. Now if I use 60, start breaking that down, that's 2 times 30. That's 2 times 15, and 3 times 5. So if I break this down, this is 2 squared times 3 times 5. Now, what's common? Well, there's no 5 in the 128 term. There's no 3 in the 128 term. The only thing that's common are the 2's. Well, how many 2's are common in both? Well, I know that this has 2 squared in it, so there must be 2 squared in here, because I have 2 to the 7th. So what's common is 2 squared, and the GCF is the number 4. That's the greatest common factor of 2. So now what we're going to do is use some algebraic terms and state the GCF. We'll start out with a numerical example once again, and we just found out that 60 broke down into 2 squared times 3 times 5. Now let's deal with the 75. That's 3 times 25, and 25 breaks down into 5 and 5. So 75 is equal to 3 times 5 squared, and we want to find the largest number such that it goes into the two numbers. So you'll notice there's a 5 here, and 1 5 here, and there's a 3 here and a 3 here. So my greatest factor is the product of the 2, or 15. Now the rest are algebraic examples, so we're going to have to take a look at what's common in both. Now, I have x's in each of the two monomial terms, and the question is, how many of those x's are in common? Well, this has 3 x's, this has 10, so it must have 3 in common. And in terms of the y's, this has y multiplied by itself 3 times and y multiplied by itself 2 times. So y squared is the common term here. And our GCF is x cubed y. Now, in this next example, we have, again, 2 numbers, and then we have variables that we have to deal with. Now, if I want to find the GCF of 40 and 64, I need to find the largest number that goes into both of those two numbers. And it would help if you can start just getting some number familiarity and be able to do some of this in your head. So I know, in this case, that 8 goes into both these two numbers. and that's going to be my largest factor in common of those two numbers. I know I have x to the ninth and x to the seventh, so x to the seventh is in both. I have a y and a y squared, so just one y is contained in both. There's no z in both, so I can't list that as a common factor. Finally, we have to state the GCF of this term. Between 8 and 12, I know 2 go into both, but also 4 go into both. And 4 is a bigger number than 2, so 4 is my GCF for the numerical part. I've got a to the 4th and a to the 7th, which means there's 4 a's in common. And then I have b to the 8th and b to the 10th, which means there's 8 b's in common. And there's my GCF. I stated in the start of the lesson that factoring is really the reverse of the distributive property. So if we look at this example and take 5x times 3y, I get 15xy, and 5x times 2 is 10x. Well, you'll notice, since we just got done talking about greatest common factors, if I look at that 15 and 10, the greatest factor that goes into both of those is a 5, and then there's an x in common. Now, if I want to do a distributive property and get this back, I say, well, 5x times what is 15xy, and I need a 3 and a y to do that. And then I need an addition to get my 10x, and I'd have to add 2. This is the factoring of this binomial. Likewise, you'll see over here that I have a product of a monomial and a binomial, and when I distribute that out, I get this term to the right. Between 16 and 24, they have a greatest common factor of 8, and then x, because there's one x in common in both. What remains is the GCF factoring from that sum of the two monomials. So what we're going to do is we're going to start going backwards now. I want to factor each of these two terms using greatest common factors. So I look at the two numbers in this case, 6 and 27, and I know that they have a 3 in common. There's no a in the 27, just in the 6, so I know that this 3 is my GCF. Now what I have to do in order to find out what term multiplied by the greatest common factor is going to get me 6a plus 27, I have to say 3 times what is 6a? Well, 3 times 2 is 6, and I need the a term, so I keep that in the problem. Then I'm going to have an addition, and I have to say 3 times what is 27? It's going to be 9. And this is my factor term for 6a plus 27. Let's do the next example. I have a trinomial in this case, and I have coefficients of 4, 3, and 5. Now, if I look for a greatest common factor between those three numbers, there isn't one that exists. The only thing that's common in this term is the x's. I have an x to the 6th, x to the 4th, and x squared. How many are in common in both? Well, it's clear to see that x squared is the smallest, so that's got to be the greatest common factor. So x squared is our GCF in this case. And then I have to get this term back by multiplying with the distributive property. So I say x squared times what is 4x to the 6th? Well, I need the 4. And x squared times what is x to the 6th? Well, we know when we have the same base of x, we have to add the powers. So 2 plus 4 is going to be 6. Then I need a subtraction, and I'm going to need a coefficient of 3, so I'll add that in. And now I need to say x squared times what is x to the fourth, again by adding principles of exponents. I need an x squared. And then I say, alright, well I need to get x squared to multiply to negative 5x squared, which means I need a negative and a 5. And then what is my variable term? Well, if I multiply x squared times 5, I get 5x squared, so there's no need to put any variable next to the 5. This is my factored form of the trinomial. Let's move down to this next example. I notice I have m's and x's. How many m's are in common in the two monomial terms within the binomial? I have 1m in common between the two. And then how many x's are in common? I have 3 here and 4 here, so 3 must be in common. And then I'm going to need to find a term that multiplies to mx cubed, which will give me my original binomial back. So m times what is m squared? Well, that's just an m. And then x squared times what is x cubed times what is x cubed? Well, I don't need anything because x cubed times 1 will do that. M times what is m? It's already there, so I don't need anything. And x times what is x to the fourth? That's just an x. By distributing this through, I get my original term back. Mx cubed is my GCF, and this is my remaining multiple. Let's move on to the next example. I need to find a GCF between 20, 15, and 10. Well, I know that in each of those numbers, 5 goes into those, and that's my biggest factor in terms of numbers. When I look at the variables, I have an a to the fifth, an a to the fourth, and an a squared. A squareds in each of those. And then I have a d cubed, d to the seventh, d to the ninth. So d cubed would be the biggest term in each of those. I now have to figure out what I must multiply this monomial by to get this trinomial back. 5 times what is 20? That's a 4. A squared times what is a to the fifth? That would be a cubed. D cubed needs nothing to multiply to get d cubed, so I leave that term as is. I'm going to need an addition. 5 times what is 15? That's 3. A squared times what is a to the fourth? That's a squared. D cubed times what is d to the seventh? I need 4 more d's, so that's d to the fourth. I need an addition. 5 times what's 10? It's going to be 2. A squared times what is a squared? Well, that's just itself, so I don't need anything to multiply. And d cubed times what is d to the ninth? That's d to the sixth. And that's my factoring. So this next problem is much more difficult. In this case, you're asked or given directions to factor, but it looks like a distribution property. Well, that's not the case. In each of these terms, you'll see there's a common multiple. This says 5 times the quantity of x plus 3, and this says y times the quantity of x plus 3. So the GCF in this case is really the binomial x plus 3. So if I factor the GCF out, I say, well, x plus 3 times something is going to give me this term back. So what must I multiply x plus 3 by to get my original term? X plus 3 times what is 5 times x plus 3? Well, that's simply 5. And then I'm going to need an addition. So I say x plus 3 times what is y times x plus 3? And that's just y. So really, this factoring can be broken down to x plus 3, which is my GCF once again, times 5 plus y. The next example is very similar. You see that it appears to be a distribution problem. However, they've given us the directions of factoring, so we must find a greatest common factor between the two terms. You'll notice this is 3m squared n times the quantity of a plus b minus the quantity of a plus b. This is a little more difficult to see because we don't see two multiplications. However, you'll notice that there's really a negative 1 right in front of this term here. So in this case, a plus b is my common term, or my GCF. So if I factor out that GCF of a plus b, and then say, well, a plus b times what is 3m squared n times a plus b. This is 3m squared n. And then I ask, a plus b times what is negative 1 times a plus b. Well, that's just negative 1. And I'm done. So that's a plus b times 3m squared n minus 1. And there's my factoring of that term. Now we're going to talk about something called factoring by grouping. We had been doing greatest common factoring. Factoring by grouping involves what it actually says: splitting up a term into two separate groups. And within those two separate groups, try to split them so that there are some common terms in each group. Now you'll notice the way I've split this up, I have my first two terms grouped because they have x's in common. And then my second two groups, or my second group actually, is split up because there's a 3 in common. If I do a GCF factoring on both, you'll notice I get x, because that's my GCF within this first grouping, times y plus 2, plus, have to keep that addition sign in the middle. 3 is my common term here, and then 3 times what is y, that's y, and 3 times what is 6, that's 2. Now, you'll notice what I have left is I have a term in which there's another greatest common factor. So I could actually factor out that y plus 2 and say y plus 2 times what is x times y plus 2? That's just x. And y plus 2 times what is 3 times y plus 2? That's just 3. So this term is my completely factored version of my original. Factoring by grouping is basically two GCF factorings. So in this next problem, we're asked to completely factor once again. And we have 4 terms, which means we're probably going to look to factor by grouping. So I need to find groups that have common terms in them. Well, I've got a couple options I can explore here. I see that there's an a in these first two, but there's nothing in common in these second two. But then I look and I say, hey, here's a 2, and here's a 2, and an a and an a. I'm going to try grouping these. And then I see a 5 here, and a 5 here, and a b here, and a b here. I'll group these guys. So let's find our greatest common factor with the groups of 2. So I have a 2 in common and an a in common. And I need to say, well, 2a times what is 2a squared? That's just a. Then I'm going to need an addition. Plus 2a times what is 2a? Well, that's just 1. Going to need to add again. Then I need to find the GCF of 5ab and 5b. Well, there's a 5 in common in both, and a b in common in both. And then 5b times what is 5ab? That's just a. And 5b times what is 5b? Again, that's just 1. And you'll notice once again that we have a common term of a plus 1. So I can use that as another GCF and factor a plus 1 out. Say a plus 1 times what is 2a times a plus 1? That's just 2a. And then a plus 1 times what is 5b. That's just 5b. And there's our factored term. Next, we'll see that we have two terms here that appear to have x's in common. And then there's a 6 and a 4, which also has a factor in common. So I'm going to group these two here. And then I have a 15 and a 10, which we know has a number in common, or a factor in common. So I'll group those two. Within the 6 and the 4, there's a 2 in common. And within the x cubed and the x squared, there's an x squared in common. And 2x squared times what is 6x cubed? That's a 3 and an x. 2x squared times what is negative 4x squared? That's a negative 2. I need my addition. And between 15 and 10, there's a 5 in common. And 5 times what is 15x? That's 3x. And 5 times what is negative 10? That's a negative 2. And once again, you'll notice the 3x minus 2 is in common. And I'll pull that out as my GCF. And 3x minus 2 times what is 2x squared times 3x minus 2? That's just 2x squared. 3x minus 2 times what is 5 times 3x minus 2? That's just 5. Alright, the next thing we're going to talk about is what's called a zero product principle. And it's really pretty straightforward if you think about it. It says if two or more terms multiply to equal 0, then one of those terms has to equal 0. In other words, it's a little easier to look at. Here's two terms, a times b, multiplying to equal 0. If this has got to be true, then it must be the case that either a is equal to 0 or b is equal to 0. There's no other way possible for that to happen. Likewise, if I have three terms multiplying together to equal 0, then either a's got to equal 0, b's got to equal 0, or c's got to equal 0. One of those three. They could all equal 0, but one of them has to be that case. This is only going to be true when I have a multiplication of terms equaling 0. It will never happen, for instance, if I had something like a times b equals 1. Sure, a and b could equal 1 to get this to happen, but what else could happen? I could have 9 and 1/9 equaling 1. I could have 3 and 1/3 equaling 1. There's a whole slew of things that could multiply together to equal 1. But if two things multiply to equal 0, the only way that that happens is if one of those two terms is equal to 0. So what we're going to do is we're going to take this product of two terms, 2x plus 1 and x minus 9, know that that's equal to 0, and try to solve the equation. Well, I know if two terms, this is like my a and my b, multiply to equal 0, then either 2x plus 1, that's my a term, has to be equal to 0, or that second term, x minus 9, has to be equal to 0. Now what I have is I have two separate equations that I can solve. In this case, I subtract 1 and divide by 2, getting x equals negative 1/2. And in this case, I'll add 9. So x equals 9. So if I wanted to solve this equation here, I know I have two possible solutions. X could equal 9. If x equals 9, then notice what happens. I have 2 times 9 plus 1 multiplied by 9 minus 9, and that should equal 0. And it does, because 9 minus 9 equals 0, and 0 times anything is 0. So this one checks off. How about that negative half? If x equals negative half, then I have 2 times negative 1/2 plus 1 multiplied together to 1/2 minus 9, and that's supposed to equal 0. Well, take a look. 2 times negative 1/2 gives me a negative 1 plus 1 multiplied by a half times negative 9. But I know that negative 1 plus 1 is 0, and 0 times anything is 0, so this checks as well. So my solution for the problem is 2. I have x could equal negative half, or x could equal 9 to make that true. Let's do a couple more. In this case, I have two terms multiplying together to equal 0. So this is the zero product principle staring at us right in the face. And if I know two terms multiply to equal 0, then one of those two terms has to equal 0. If I solve the term on the left, I divide by 4, and I get x equals 0. Or I can add 7x to both sides, get 5 equals 7x, divide by 7, and get 5/7 is equal to x. Clearly easy to see that when I plug 0 back in, I get 4 times 0, which is 0 times anything is 0. Not a problem. This next one might be a little bit more difficult, so we'll work that out. 4 times 5/7 times 5 minus 7 times 5/7 better equals 0. 4 times 5/7 is 20 over 7. And then I have 5 minus 5. 5 minus 5 is 0, and 20 over 7 times 0 is 0. So it checks out. So my answers are x equals 0 or x equals 5/7. Now in this problem, it's a little bit different because I have an x squared term and an x term, and these are not like terms, so I can't combine those together. But I notice that it's possible to see a GCF in here. 3 and 12 have a greatest common factor of 3, and x squared and x also have a greatest common factor of x. Then I can say 3x times what is 3x squared, that's just x, and 3x times what is negative 12, which is negative 4. Now you'll notice I have a product of two terms, call them A if you will and B, multiplying to equal 0. So now this is a zero product principle, and I can say, well, 3x could equal 0, or x minus 4 could equal 0. Therefore, dividing by 3 to both sides, I get x equals 0. And in the second set of numbers, I can just add 4 to both sides, and x would equal 4. And this one's a lot easier to check. If I plug 0 in, 3 times 0 is 0, and 0 times anything is 0. In this case, I have 3 times 4 multiplied by 4 minus 4. And 4 minus 4 is 0, and 0 times anything is 0. So it checks. Now, again, this problem is a little more difficult because I don't have either term set equal to 0. So what I must do, if they're asking me to solve for this, is I must set the whole equation equal to 0. In fact, when you see a squared term and a non-squared term in the same problem, the best thing to do is always set the equation equal to 0 and look to factor if possible. So I'm going to add 12x to both sides. Now, as we stated earlier, there is no way to combine these two terms. So this is really just x squared plus 12x. We know negative 12x and positive 12x is equal to 0. And then I have a GCF in common. I see there's an x squared here and an x here, giving me an x in common. And then I ask, well, x times what is x squared? That's just x. And x times what is 12x? That's just 12. Set that equal to 0. Use my zero product principle. X equals 0. Or x plus 12 equals 0. Subtract 12 from both sides. And x could equal negative 12 as well. So my two answers are 0 or negative 12 for this example. That's really all we've got for you today. There was a lot in this lesson. Write your lesson summary out, describe what you understood and didn't, and solve these problems, and we'll get back to you tomorrow. Okay?